and matching in particularly in bipartite graph. So first of all, what is a matching? So matching is basically a set of edges such that every vertex is incident to at most one edge. So matching is basically some subset of edges satisfying this property. So in this example, see, it is a bipartite. So matching can be defined for any graph, but in particular, if we are talking about this bipartite graph, we can see that uh, AD CB. This is matching. This is a matching because every vertex is incident to at most one edge. So E and F are we can see that in these edges no vertex is adjacent to more than one edges. And similarly, if we look at BC and DE, this will also form a matching. And and similarly CF and AD will also form a matching. Now, can anyone tell me why this AD, if we look at AD, BC, and CF, if we look at AD, BC, and CF, why won't they form a matching? So,
Because in AD there is a one edge from C also, CD. So
hmm,
that is why this AD is not a matching one.
no, no. So I'm AD is not a so I'm this is some set A. So now you have to say why these three edges does not form a matching. So what is your reason?
Ma'am, the requirement for a matching is that the vertex should be used at most once. Here C is used twice,
Yes.
so it
It,
won't be a match.
yes, exactly. So here you see, if you look at the edge BC and CF, the vertex C is adjacent to two edges. But the requirement for matching is that it should be adjacent to at most one edge. So this vertex C is violating this property. Therefore, this is not a matching. So is the definition of matching clear to everyone?
Yes.
Okay. Okay. So now So now, given a matching, given a matching, we can talk about an augmenting path. So augmenting path for a matching M will be an alternating path between matched and non-matched edges. So if you are given a matching M, then these edges contained in that matching will be called the matched edges, and all other edges except that matched edges are the unmatched edges. An augmenting path refers to an alternating path between matched and unmatched edges. So it should start and end with an unmatched vertex. So there are two requirements for augmenting path. First, it should be an alternating path between matched and non-matched edges. That means that if you have a unmatched edge, then after an unmatched edge, the other edge that is coming in the path should be a matched edge, and after matched edge, it should be an unmatched edge. And the second requirement is that start of the path and end of the path should be with an unmatched vertex. So such a path with these two properties is an augmenting path. So in this above example, you can see if I am taking the first matching M1 as ADCB, then EF will be an augmenting path because E is a so in this, yeah, so I have AD and CB. I have AD and CB. So matched vertices are A, C, B, and D. So an augmenting path should start from an unmatched vertex. So it should start from E or F. And secondly, it should also end with an unmatched vertex. And it should alternate between matched and non-matched edges. So if you see just the edge EF, it is, if you look at this path EF, it is starting with an unmatched vertex, it is ending with an unmatched vertex, and since it has just one edge, it is alternating, it is trivially following this condition, that alternating path. So we see that for M, P1 is a P1 is a alternate augmenting path. Similarly for M prime, if we look at M prime as BC, if our M prime is BC and DE, so an augmenting, so we see that FE, ED and DA is an augmenting path. So here F is an unmatched vertex. Then we are starting with an unmatched edge, which is FE. Then ED is a matched edge. Then DA is a non-matched edge in this matching. And A is also a unmatched vertex. So this path is also satisfying that property. So therefore it is an augmenting path with respect to M prime. Now I am taking my third matching is M prime as CFAD, which is this ADCF. So can anyone of you give me an example of augmenting path for this matching? So this is the graph, this is the matching, the highlighted pink edge, and you have to give me an example of any augmenting path with respect to M double prime. So what is the property? It should, so first of all, what are the matched vertices in this matching?
EFFCCD
Okay, you gave me a path which is EF
FC
FC. Okay, EFFCCD.
CD.
So, yes, this is a path. Right, good. EFFC and CD. Why? Because it is starting with an unmatched vertex, ending with an unmatched vertex. Oh no, it is not an augmenting path. It is not ending with an unmatched vertex. D is a matched vertex. So, this cannot be an augmenting path. So,
CB. Instead of CD, can we have CB?
yes, if we write CB, then it is fine. So did you so whoever gave the example, did he understand why CD EFFCCD is not a augmenting path? EFFC and CD. This path is alternating between unmatched edges, matched edges and unmatched edges. But it is starting with an unmatched vertex but D vertex. So it is a part of a matching. Therefore it is a matched vertex, but it is not ending with an unmatched vertex. Therefore this is not an augmenting path.
Yes, got it.
The other example which is EFFCCB. Now this path is satisfying all these two conditions. It is starting with an unmatched vertex, ending with an unmatched vertex, and it is alternating between unmatched and matched edges. Therefore it is indeed an augmenting path. Okay, now, okay, so now the next part is, once we understand matching, what is maximal matching? Maximal matching will be a matching which has maximum number of edges. And there is this theorem that if matching M is maximal, if and only if there are no augmenting paths with respect to that matching. And so this was done, we won't be doing the proof because this was done in the class, but it is an important theorem. So remember that if you have to say some matching is maximal, and if you can give an argument that there is no augmenting path with respect to matching M, then you can say that that matching is a maximal matching, and it is a necessary as well as a sufficient condition for maximal matching. And then we have okay, then we have perfect matching. So what is a perfect matching? Perfect matching is a matching that covers every vertex of a graph. Okay, so that is a perfect matching. So in this example, are any of these matching perfect? In this, so we have M1, M2, M3. Are any of these matching perfect?
No.
No, no, ma'am. No.
Why?
Because you said all, it should match with all vertex.
Yes, it should cover all the vertices.
So
Ye-
if we can make perfect matching in this example.
okay, so can you give me an example of perfect matching then?
A, B, C, D, E, F.
Yes, A, B, C, D, E, F. So so M1, M2, M3, they are not perfect matching because they are covering only 4 vertices, but this graph has 6 vertices. So they are not covering every vertex.
Ma'am, can we say that perfect
But this,
matching? Ma'am, can we say that perfect matching is maximum matching? No.
yes, if a graph has perfect matching, then it will obviously be a maximal matching. But the thing is, a graph need not have a perfect matching. This graph has a perfect matching, but a graph need not have a perfect matching.
So if we find a perfect matching of a graph, that means that matching set is the maximum one.
Yes. So, yes, that is true. If you can find a perfect matching of the graph, that will be a maximal matching. But, okay. So, the concept of maximal matching is important when we don't have a perfect matching. So, if we don't have a perfect matching, the best we can do is to find the maximum matching. Then, then we did the and for Hall's theorem, Hall's theorem gives us a nice condition for bipartite graph to have a perfect matching or not. And it is a more general result, in a sense that if we are given a bipartite graph, then it will have two bipartitions, x and y. Then this theorem is giving us a necessary and sufficient condition to for a graph to have matching which saturates x or y. So first of all, what do we mean by that G has a matching that saturates X? That means G has a matching that saturates X means that a matching which covers every vertex in X. If we are saying a matching saturate X, we means a matching which is covering every vertex of X. So now Hall's theorem is giving us a nice condition. It says that it will have a matching that saturates X if and only if we take any subset S of X, any set of vertices in X, then the order of S should be less than equal to the order of neighbors. So first of all, what do we mean by neighbors of S? Neighbors of S mean, neighbors of S means that suppose in S we have vertex v1 v2. So neighbors of S means we look at all the vertices which are adjacent either to v1 or v2. So let's understand this neighbors of S with an example. So suppose if S is A, neighbors of S will be all the vertices which are adjacent to A. So it will be basically A. So in this case, it will be just B and D. And if S is equal to FA, we are looking at the vertices which are adjacent either to A or F. So in this case, we see they are in this case it is B, D, and G. So did you understand what do we mean by neighbors of S? If yes, so first of all, if S is equal to C, what is the neighbors of S?
B,
B, E.
B, D, and E.
Good. And what about the last one? Neighbors of AC. This one.
B, D, E.
B, D, and E. Okay. So these are the neighbors. So Hall's theorem is saying that if order so first of all, you see one side of this theorem is very easy. Suppose if we have this, our, we have this simple graph, this x y, we have this bipartite graph, and I take my s, and I take my s to be ab. So in this case, neighbor of S is 1, which is just C. So we see that order of S is greater than neighbor of S. And can this graph, so now, so this is violating this condition. Can this graph has a matching that saturate X? That is, can you have a matching which will have vertices A and B? Is it possible? Is it possible in this to have a matching that saturates X?
No, ma'am, no.
Why?
Because S is 2, that cardinality of S is 2, and NS is 1. So, but if there is a bipartite, this is also bipartite graph. So, S mod S should be less than NS.
Yes, yes, that is the statement of theorem. So I was trying to prove this theorem one condition, like this condition, that if it is G has a matching that saturate X, then order S should be less than equal to NS. So without using the theorem, can you tell me why cannot, without using this theorem, can you tell me why this graph cannot have a matching which saturates X?
Because A and B, if we see, degree is 1 and C has degree 2.
Yes, so
In fact, C is saturated, not A and B.
yes, we can, because if we, so if we have some S here and NS here, and order of NS is less than S, so we can so if we pick a distinct neighbor for each S, if we pick a distinct neighbor or for each S, but order of S is, order of S is order of S is less than neighbor of S, then we will be left with some elements of S with which we cannot match any neighbor. So in this case also, suppose if we choose AC to be our matching, then we have no neighbors left for B to match. Therefore, so this condition is obvious, that if G has a matching that saturate X, then this should be satisfied. But the beauty of this theorem is that it is a necessary and sufficient condition. That is, it is the uh, uh, converse of this is also true. So this was Hall's theorem. So did everyone understand the statement of Hall's theorem? Is there any doubt in the statement of Hall's theorem?
Ma'am, Hall's theorem is general or it is for bipartite graph?
It is for bipartite graph. It is not for, it is for bipartite graph. Need not be true for general graph. Okay. Okay. So now if the statement of Hall's theorem is clear, then let's look at some problems. So question 1 is, suppose M1 and M2 are two matchings of G, and size of M1 is strictly greater than size of M2, then you have to tell me if it is true or false. That first statement is G has an augmenting path with respect to M2. Is it true or false?
It is true, ma'am, true.
Does everyone think it is true?
I think no, false.
So there so okay, so why do you think it is false?
Uh, if like both are matchings, right?
Yes.
So if uh, can I say that M1 is an augmenting path without loss of generality?
Uh
Augmenting matching without loss of generality.
what is augmenting matching?
Oh yeah.
Ma-
So I am saying that if M1 is a argu is it has an augmenting path like M1 has an augmenting path, it means it is unmatched, matched, unmatched.
Okay.
It would lead that M2
Madam, since M2 is less than M1,
Yes.
so
Yes.
then there must be a augmenting path because we have still increase one set which can increase M2. So that is M1. So with
Okay.
that theorem, we say that there is a if there is a one set which is bigger than M2, so that definitely there is an augmenting path.
Okay. Yes, you are correct. So what is he saying is he's using this theorem that M is a maximal matching. M is a maximal matching if and only if there are no augmenting paths with respect to M. So so M2, so since we have a matching which is bigger than M2, that means M2 is not a maximal matching. And if M2 is not a maximal matching, then by this, since this theorem has a necessary and sufficient condition, that that no augmenting path with respect to M, therefore it should have an augmenting path, because if it has no augmenting path, then it will become a maximal matching. Since M2 is not a maximal matching, therefore there is an augmenting path. So is everyone clear why it is true? So we are directly using that theorem. So Miransh, is it clear?
yes.
Okay. So now what about 2? G
Ma'am, it is
has so the
false.
G has no augmenting path with respect to M1.
Ma'am, it is false.
Okay. Does everyone think it is false, or anyone think it is true also? Okay. So why it is false?
Ma'am, because in this question it is not written that M1 is maximum matching. It is just written that it is a matching. So if we take M1 as a maximum matching, then definitely no augmenting path with the same theory.
Yes. Yes. So he's correct. So we are not given that M1 is a maximal matching. There can be a matching bigger than M1. Therefore, we cannot say that it has no augmenting path. It may or may not have augmenting path. Therefore, this statement is false. Now, the second question is augmenting path with respect to any matching has odd length. True or false?
True, ma'am.
Does everyone think it is true? Everyone think about it. So what is an augmenting path? Augmenting path was a path which was starting augmenting path was a path which was starting and ending with a unmatched vertex, and it was also alternating between unmatched, matched, unmatched, matched. So now now can such path be of even length, or can we say that such kind of path will always be of odd length?
Such type of path is always the odd length.
Yes. Okay, so there is an answer that it is true. So the answer is correct. It is true. But now, can everyone think why it is true? Just by the definition of augmenting path, why it is true that augmenting path should have odd length? Okay, Anupam, why do you think it should have odd length?
Ma'am, if you see the sequence
Hmm.
unmatched, match, unmatched, then match.
Hmm.
So if you okay stop at unmatch, so then all that path will always be the odd. If you increase one length, so
Hmm.
it will even then it will become cyclic.
Okay. Yes. So basically, or argue. Yes, you're correct. So second part is also true. Second part is also true because augmenting path is an alternate path. First of all, alternate path unmatched between unmatched edges, unmatched, matched, unmatched, matched, unmatched, matched. Also, since it is starting with an unmatched vertex and ending with an unmatched vertex, so the initial edge would be an unmatched edge and the last edge will also be an unmatched edge. So you see that we all will the augmenting path, it is starting with an unmatched edge and ending with an unmatched edge, and it is alternating between unmatched and matched edge. Therefore, it should have odd length. So, is it clear to everybody why augmenting paths should have odd length? Because we have to start with an unmatched vertex and end with an unmatched vertex. Okay. So now, third question is, if G is a bipartite graph and if G is k regular, then order of x should be equal to order of y. So what do you think? Is it true or false?
It is true, ma'am.
Okay. Others, what do you think, it's true or false? You can also, if you don't want to speak, you can write in the chat box also if you think it is true or false. Okay. So why is it true?
And the k regular graph, that means every node in X has connection with Y, and similarly from every Y, there is a connection in X.
Hmm.
So in that case, the node in X and node in Y is same, man. Then only it will happen.
Okay. But why will that happen? Why? So you're right. Every edge has one vertex. Every edge has one vertex in X and one vertex in Y. Has one vertex in X and one vertex in Y.
In k regular graph.
Anyway, in this is true for every bipartite graph, right? That if you have a bipartite graph, every edge, so you have every edge will have one vertex in X and one vertex in Y.
Yes.
So
Yes.
this is true for every bipartite graph. Now, why, if it is k regular, then this will say that order X equal to order Y. So first, can we say this? Degree V belongs to X is equal to degree W belongs to Y. If we sum up all the degrees, so we have this graph X to Y. if we sum up all the degrees of vertex in X, this is my LHS. And now we have Y. If I sum up each degree in Y, can we say that these two things will be equal?
Yes.
If yes, why?
Because ma'am, for K regular it is yes. For other it needs to be.
Ma'am, if the degree vertex is same, if we assume if we take a vertex in X, then and we make its degrees k degrees, then we basically are joining k vertices. uh, it- Taking that vertex from X, we are joining k vertices from B. We,
Okay.
and we will be doing it for all the vertices in A
Yes.
and doing the same with B.
Yes.
So if assuming we are leaving few for that vertex, when we come to B and make its degrees, it degrees needs to be K only. So we would be leaving the same amount of vertices in A. That is why the number of vertices should be same. It is
Okay.
basically, I'm trying to
Yes.
say that it is an optimization kind of a thing where you have, if you are assuming there are six vertices, three in A, three in B, and we take 1 degree from A, join it with two vertices, leaving
Yes.
one in B.
Yes. Okay. So you are
And
saying we have three vertices. Yeah.
yes,
So now you are saying if we start with joining with this. Yeah.
I'm saying that leave any one vertex from B.
Okay.
Or we can even take it three vertices, but it would be a complete graph. So we would lose that generality. So leaving one in B, uh, doing the same for all the vertices in A,
Okay.
and when we will come to B, we have to do exactly that, right? We have to make sure it
Ma'am,
is a K regular
ma'am,
graph. So
Okay.
ma'am,
it
each
becomes more like an optimization thing.
But like, so your argument is bit incomplete. So I don't get it. Why? How can you conclude that if we start we if so for one vertex we are joining k vertices, right?
Yes,
Then for other vertex we'll also join k vertices. So
yes.
if the other set, so like, why are you saying that we'll leave something?
Uh, I am saying uh, I am saying that if we join every graph, it would be if we join every point, then it would be a complete graph, right?
Yes.
From
Yes.
A to B.
Yes.
So
That is true.
we will lose the generality of this statement because it is a k regular graph. So I am
Okay.
saying join two vertices or n minus k vertices. Uh, so
madam,
we have
ma'am,
to do the same thing for every
Okay.
vertex.
Okay.
ma'am,
This.
each edge
Yes.
contribute the degrees
Yes.
So
Okay. Okay.
twice.
in from the
So
first
Okay, wait, Miraj. Let
sorry,
Vinayak. Yes, you continue. Yeah.
ma'am,
Hmm.
each edge contributes the degree sum
Yes.
because the edge is the end of one set is one vertex set in V
V
and another in
one.
V2.
Yes. Yes. Yes.
So
Okay.
the degree sum is
Okay. Yes. So what is he saying is basically, so he is saying that since every edge has one vertex in X and one vertex in Y, LHS is equal to number of
in
edges,
YS.
and this is also equal to number of edges.
Yes, ma'am.
So therefore, the degree sum in X and degree sum in Y is equal, and this is true for any bipartite graph. For this statement, for first two statements, we don't need that our bipartite graph is k regular. This will be true for any bipartite graph, isn't it? Because
Yes,
any
ma'am.
edge has one vertex in X and one vertex in Y. So each edge is contributing degree 1 to exactly degree 1 to degree in vertices in x, and degree 1 to degree in vertices in y. Therefore this total sum of degree of vertices in x is equal to total sum of degree of vertices in y for any bipartite graph. This is what this. So now, did everyone understand his argument?
Yes, and that is equal to n by 2 if we extend this
Yes, that is equal to no wait, n by 2 y what y n by 2.
for this bipartite k regular graph.
So what is n?
N is the total number of vertex.
Huh. So if n is a total number of vertex, so this so y no, if n is a total number of vertices, why it will be n by 2. So this so now no, that need not be true. So can you compute this? What is LHS? Degree v belongs to x. So we are given that this is a k regular graph. So can you compute LHS? What is LHS? So now this is true for first statement is true for any bipartite graph. Second statement is true for any bipartite graph. Now suppose my bipartite graph is k regular. That means degree of each vertex is k. So what is this sum equal to?
Mod x into k.
Yes, mod x into k. And what is RHS equal to?
RHS is k into mod y.
K into mod y. And by mod x or mod y means size of x. And
Yes.
we know that LHS is equal to RHS. That means mod x k is equal to mod k y. So k get cancelled with k, and we get that mod x is equal to mod y. And this is what we were requiring. So is everyone clear that if we have a k regular bipartite graph, then the number of vertices in both the bipartitions should be equal? Is it clear to everyone?
Yes.
Okay. So now the second the second statement says that bipartite graph has perfect matching if and only if it is k regular for some k greater than 0. True or false?
True.
Okay, so you are saying it is true. So everyone thinks it is true?
And please explain that statement, ma'am.
Huh. So
How it
the
is true?
no. Right now I'm not saying it's true. I'm asking if it is true or false. So the question, so our theorem says that if a bipartite graph is k regular, then it has a perfect matching. But this statement is saying that bipartite graph will have a perfect matching if and only if it is k regular. So one implication we know that if a bipartite graph is k regular, then it has a perfect matching. But is the other condition true or not? If the other condition is also true, then we can say that this statement is true. But if the other condition is not need not be true, then the statement is false. So what do you think? Can we say that if bipartite graph has a perfect matching, then it has to be k regular?
No, false, I think. Uh,
Okay, so there's
there
one false.
True,
Anyone?
ma'am. True, true.
So you are saying that a bipartite graph can have perfect matching only if it is a k regular graph.
is this question for
Yes,
me?
ma'am.
Okay. So okay. So somebody said false. So do you have do you think it's false?
Yes.
So can you give an example?
Yes. Mm,
Yes. Okay.
make.
So,
make uh,
how many vertices on the first set?
uh, uh, make a vertex join and in left, upward, and right direction you can make three vertices.
Okay,
Um,
three vertices.
join them. No. Oh, shit. We are talking about three regular graphs.
No, no. We are talking about question 4 right now.
Oh,
That is, yours. So the question is, so we know that if a bipartite graph is
mm,
k regular, then it has a perfect matching. Now, question is if the converse is true. That is, if a
mm.
bipartite graph has perfect matching, then it has to be a k regular graph. So we are saying basically, if a bipartite graph is not k regular, then it cannot have a perfect matching. If we are saying this statement is true, we are basically saying that. And if you think it is false, then you'll have to give me an example of bipartite graph which is not k regular but has perfect matching.
K22. Um, Sorry, ma'am.
K22 will be a regular graph. K22 will be a regular graph. But you are on right track. K22 is
K-
K22 is a regular graph because degree of each vertex is 2.
okay,
So you can
but we
modify it
can
slightly.
not not complete, ma'am. Non-complete. You put two bipartite A
Okay.
and B, four vertices,
Yes.
two vertices on A and two on this side,
Yes.
and well, if you have one edge
Yes.
and two edges from this side,
Yes. So you are
it
saying
is
this,
a
right?
perfect matching. Yes, ma'am.
Yes. So yes. So very good. So this is an example of a bipartite graph. It has a perfect matching, right? We can just take these two edges. But this is not k regular because this has degree 2, this has degree 2, but these two vertices have degree 1. So it is not a regular graph, but it has a perfect matching. So the converse of the statement is not true. We only have that if a bipartite graph is k regular, then it will have a perfect matching. But the other way around is not true. That if a bipartite graph has perfect matching, then it has to be k regular. It is, so we can see by this example. So is this question clear to everyone? Any doubts in this? So basically the
Yes.
fourth is false. So fourth is false. Okay. So now if there are no doubts for fourth question. So fourth question was saying that a k regular bipartite graph will have a perfect matching. Now fifth question is more general. It is saying that three regular graphs have perfect matching. So is it true or false? So we know that a bipartite graph, if a bipartite graph is regular, then it will have a perfect matching. But that can we say in general that a general k regular graph will also have a perfect matching? True or false? So what do you think? So does everyone understand the fifth question?
Madam, fifth is true, ma'am. Because in K regular is bipartite graph.
No, no. But
Is
yeah, yeah. So in this question, I am not saying that the graph that is given is bipartite. I'm just saying three regular graph. Ha-
oh,
if it was
Mm,
bipartite, then it would have been true.
Sylvester's graph would be the counter example here.
Yes, yes, very good. So Sylvester graph is a three regular graph, but it is does not have a perfect matching. So I'll just draw the graph. Up. So if you see this graph, okay, sorry, bad drawing. So if you see this graph, this is what is known as Sylvester's graph. So this is a three regular graph. But in the next lecture, in the next, when you'll be studying general matching, you'll be studying our theorem. So we have this Hall's theorem, which is giving us necessary and sufficient condition for bipartite graph to have perfect matching. Then there's this Tute's theorem, which will give necessary and sufficient condition for general graph to have perfect matching or not. And from that theorem, which you will be doing in the next lecture, you will be able to see that this graph will not have a perfect matching. So but it is three regular. So the point of this question is, so this is false. So the point is that we have that k regular graphs, if they are bipartite, then they have perfect matching. But if we are talking about general regular graphs, they need not have perfect matching. And the counter example is this Sylvester's graph.
What is the application of this Sylvester graph?
Application, so it is just an construction. uh, so it is just one of the graph. There is like uh, and it is serving as this nice counter example. So I don't know the, like, why it is special, but see, in this we are
Um,
getting an.
this Sylvester has made one graph to disprove this. Now, my as an engineering application, what is the application of this graph? Where we can use this?
So I'm not sure. Maybe it was just constructed to, like, so some graph may not have application, but it is serving as a counter example, right? So it is special in that manner. But so I'm not sure if it has some real life applications or not.
Okay, man. Thank you, man.
Okay, so now this was this question. So now next question. So now this is a bipartite graph, and we have nice necessary and sufficient condition to say if it has a matching that saturates some bipartition or not. So now can you tell me, if this given graph has a perfect match, has a matching that saturate X or not? So if you are saying it is no, then you have to give me a subset S, which is a subset S, which is a subset of X, such that order of S is strictly greater than order of neighbors of S. So if you can find some S like that, then you can say by Hall's theorem that this will not have a matching that saturates X. So what do you think? So
Ma'am,
okay, first of all, just say yes or no. Don't tell the set.
ma'am, uh, it X we say there are four nodes, and Y we it is five nodes.
Yes.
So definitely Y is not saturated because it has one node which is extra.
Okay. Yes. For Y it is fine, but for X, so for X also, if the you just tell me first if it answer is yes or no, or you can write in the messages. Then we'll later see what the set is. So don't speak out the set. Yes or no.
No.
Okay, so there is a no. So that means he has a set which is satisfying this condition. That is, you can find some vertices in X whose numbers of neighbors are strictly less than that S. So the answer is correct. The answer is no. Now find that set which is satisfying the condition that I have written. Everyone try find that set. And if you have an answer, raise your hand.
The set A D S is A D.
Oh,
A
okay.
D
Okay. So first, first,
A C D. The set S A C D.
okay. You were not supposed to answer the set, but okay. Uh, so okay. So somebody has raised it. So is your set also same, Miransh? So somebody raised there. So the set he is saying is A C D. S is A C D. Okay. So what are the neighbors of ACD? What are the neighbors of ACD? So this A C D. What are the neighbors of ACD?
F
F
and
G
W.
H.
Yeah. So neighbors of S are F and H. So it is satisfying this condition. Order S is 3, but neighbor of S is 2. So from by Hall's theorem, we can conclude that this graph won't have a perfect matching. So is it clear to everyone? Is it clear to everyone why this graph has no perfect matching?
Yes, ma'am. By
Yes,
Sorry,
this,
not
ma'am.
a matching which is saturating X. Yes. So Kavit.
but without this finding the set, it is visible also. Which what I said, there are x is 4 and there are y is 5.
Yes, for from y, for y it is clear without giving the set that y has 5 vertices, but x has 4. But y, for x it is not, without giving the set you cannot conclude for x, right? That it won't have a matching that saturates x. For that you'll have to give a set.
Yes.
For B part it is clear, but for A you have to give the set. So was there any question? So somebody was speaking in between. If there was there a question? Okay. So next question. Next question is, a building contractor advertised for a bricklayer, carpenter, plumber, and a tool maker and receives 5 applicants. One for a job of bricklayer, one for carpenter, one for bricklayer and plumber, and 2 applications for plumber and tool maker. First of all, draw the corresponding bipartite graph, and secondly, can all the jobs be filled by qualified people? So what are we supposed to do in this question?
First, ma'am, we have to draw the graph, bipartite graph. Then we have to see the matching.
Yes. Okay, so that much is clear. So now, yeah. So now we have, so the B part say, can all of the jobs be filled by qualified people? So what are the candidate? So what should be our bipartition? What should be set A? What should be set B?
Job and applicants. Applicants 1, 2, 3, 4, 5 one side and jobs other side.
Yes, good. So he's saying, so jobs, so he's saying applicants at one side, and there are 5 applicants. So A will have 5 set, and there are how many jobs? One, two, three, four. Bricklayer, carpenter, plumber, and tool maker. So now, one for the job of bricklayer. So first application is just for bricklayer. Second application is just for carpenter. Third job will be, third job will be for, one for carpenter. Third application is for bricklayer and plumber. So therefore there are 2 edges. and 2 for plumber and toolmaker. So fourth applicant is applying for plumber as well as toolmaker, and same for the fifth applicant. Now the second question is saying, can all the jobs be filled by qualified people? So if this is X, applicants is Y. So what kind of matching do we want? So what kind of matching do we want? Question is saying that can all the jobs be filled by qualified people? So what kind of matching we are looking for?
When we are for qualified people, we are looking for perfect matching.
But this graph has odd number of vertices. It cannot have perfect matching. So it is asking for matching which saturates either X or Y. So what is it is asking for? Can all the jobs be filled by qualified people?
So we have to saturate Y, ma'am, first.
Yes, because we are asking if all the jobs, can all the jobs be filled by qualified people. So the question is asking that for each job can we find at least one person. So do you think this bipartite graph has a matching that saturates Y? Yes or no? If it is answer is yes, then the answer to B will also be yes. So does this graph has a matching that saturates Y?
Yes, ma'am.
Okay, so there's one answer is yes. Others, what do you think? So first of all, if there's a does everyone understand the question? If there's a doubt in the question, please ask. And if you have understood, then tell if the if it has a if this bipartite graph has a matching that saturates Y. So this question is basically asking, this is equivalent to saying asking if G has matching that saturates Y. Okay, so answer is yes. So can anybody give me a perfect matching for this graph? A perfect match. Can you give a sorry, not a perfect matching, matching for a matching that saturates Y. So basically a matching that saturates Y. What is that matching? A matching which is covering all vertices of Y. So is there any matching here which is covering all vertices of Y? Okay. So there was an answer which said yes. So do you have a perfect matching, Anupam? Matching which is saturating Y, not perfect.
Uh, uh, One to brick
Okay.
and two to carpenter,
Wait,
three
wait,
to
wait. One, uh, one to brick, two to carpenter,
carpenter,
hmm,
three to plumber,
three to plumber,
and four to
tool maker.
toolmaker.
Okay. Yes. So the answer is yes. And we also have perfect matching. We also have matching that saturates Y, not perfect. So is this question clear to everyone?
This type of application is application part. It is very interesting, like this type of
Hmm.
questions.
Yes. Okay. Yes. Okay.
Ma'am, instead of 4 to tool breaker, 5 to tool breaker may be taken the matching for that.
Yes,
Is it
that is also right. So you are saying we
okay?
can consider the other matching. Yes, you can all do that. Matching need not be unique. So you are
Okay, ma'am.
saying we take this, 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 and this, right?
Okay, ma'am. Okay.
Huh.
Yes,
That
ma'am.
is also a correct answer. Yes. So a matching need not be unique. In this case, only we see that there are two matchings. Okay. So is this question clear to everyone now?
But ma'am, this is the maximum matching also.
Yes. Yes. This is a maximal matching also. Yes. So now, since you have said that it is a maximal matching, why do you think it's a maximal matching? Why we cannot have a matching bigger than this?
If we increase one more, ma'am, what you say from X to Y,
Hmm.
then there is no one-to-one mapping.
Yes. So basically, since so y has only four vertices and all the edges in so in a matching, we are not allowed to repeat a vertex. And since y has only four vertices, and all the edges will have at least one vertex in y, we cannot have a matching of more than four vertices, more than four edges. Because now if we have an fifth edge also, then it will have to repeat a vertex of y, and matching cannot repeat a vertex. Therefore, this is also a maximal matching. You are correct. So, does everyone understand this also? Why it is a maximal matching? Okay. So, if it is clear, let's move on to next question. Okay. So now this is uh inter- so now so now if a graph is big, as in like if graph has many edges and if it is not straightforward to find a maximal matching, then we have an algorithm to find a maximal matching, which is augmenting path algorithm. So I'll try to do it. So augmenting path algorithm helps us in finding a maximal matching. So what is that algorithm says? So we have to find maximal matching for this. We have to find maximal matching for both these graphs using this augmenting path algorithm. So first of all, I'll explain the algorithm and then we will solve this question. So algorithm is basically, we start with matching to be empty. Then uh, then we initialize with matching to be empty, and while there is an augmenting path with respect to m, path with respect to m, then we we call our matching m with augmenting path p with respect to m. Then m is basically m symmetric difference p, which is basically this notation is used for saying m minus p union p minus m, symmetric difference. So if you have set a, if you have set b, symmetric difference of a and b is basically this portion and this portion, a minus b union b minus a. So this is the symmetric difference. So now the algorithm says that we start with matching to be empty, and if there is an augmenting path with respect to m, then we define our new matching to be m symmetric difference that augmenting path. And we keep on doing this until we reach a matching which has no augmenting path. And if we have got a matching which has no augmenting path, then by the theorem we can conclude that it will be a maximum matching. So, any doubts in the algorithm? Does everyone understand what the algorithm is saying?
Ma'am, can you repeat the algorithm again?
Yes. So, the algorithm is saying basically we start with a matching M. Okay. We start with an empty matching. Now, if there is an augmenting path with respect to that matching, then we define our new matching as matching symmetric difference P, which is just M minus P union P minus M. And that will be our new matching. Now, once we have got that matching, suppose that matching is M1. Now we look at if there is an augmenting path with respect to that matching. If there is an augmenting path with respect to that matching, then we repeat this procedure. And we keep on repeating it until we reach a matching which has no augmenting path. And if we have reached a matching which has no augmenting path, then that matching will be a maximal matching by our theorem. So now so if you haven't understood it, let's do it with an example. Maybe then it will be clear.
Ma'am, this symmetrical difference, can you
Yes.
give this example, ma'am? Symmetry that
Symmetric difference, okay. So basically, if A is this set A, B, C, and B is C, D, E, then symmetric difference is A minus B union B minus A. So basically, first A minus B is all those elements of A which are not present in B. So what is A minus B? Just AB, right? And what is B minus A? It refers to all those elements of B which are not present in A. So this will be DE. This will be DE. And A symmetric difference B will be AB CD. So in a way, if I'm doing it within Venn diagram, if I'm like this is the Venn diagram.
CD or DE?
DE, sorry, DE. Yes, DE. So if we are looking at a Venn diagram, if we are looking at Venn diagram, this is A, this is B. Then A minus B is all the things which are in A but not in B. So basically this minus the intersect. And similarly B minus A is this. So we are taking the union and removing the intersection. So in other words, either you can write it like this or you can write it like this: M union P minus M intersection P. So is the definition of symmetric difference clear?
Yes.
Okay. Now if the definition is clear, let's okay, I'll do it in a new page. Let's use the algorithm to okay. So now this is the graph, and using augmenting path algorithm, we have to find the maximal matching. So first I am starting with M equal to empty. So now since they have no edges, can you give me an augmenting path with respect to M? So augmenting path is basically starting with a unmatched edge, starting with an unmatched vertex, ending with an unmatched vertex, and it should be alternating between matched and unmatched vertex. Now since M is empty, none of the vertices are matched. Therefore we can pick any edge. So our P is just, let's say, AV. So now my M is symmetric difference of M and P. So this is empty. An empty set and symmetric difference of empty set and P is just AV. So my new matching is AV, this edge. So now if my matching is AV, give me an augmenting path with respect to AV. Anyone? Give me an augmenting path with respect to AV. So what is an augmenting path? It should start with an unmatched vertex and end with an unmatched vertex. Yes. So,
WA,
sorry, W A
A,
W
A,
W A. Okay.
and matched vertex AV and VB.
Okay. So his path is W A A V and V B. Okay. So that is the path. That is correct because it is starting with an unmatched vertex, ending with an unmatched vertex, and it is alternating between matched and unmatched vertex. Good. So now what? Now we have a M1 and we have an augmenting path. Now we'll look at its symmetric difference. So what will be the symmetric difference? Union minus intersection. So in this case, if we so AV is the only common S. So the new matching is WAVB. So now WAVB is our new matching. WAVB. So now can anybody give me an augmenting path with respect to this matching? So if this is a matching, give me an augmenting path with respect to this matching.
XC,
Okay, XC. That's it.
then
XC. Then you have to stop at XC because there is no matched edge, right?
yes, yes, yes.
So,
Ma'am,
yes,
CVA
CV, yes,
CVVB.
VB,
No,
okay.
no, no, no. This is not correct.
Okay, there can be other paths, but this is also correct. So let's stick with this for now. Okay. So now what is the symmetric? So what is our new matching now? We have to take the symmetric difference of M2 and P2. So it will be WA, VB and XC. Okay. So now this is my matching 3. So do we have an augmenting path with respect to this matching? So can anybody give a augmenting path with respect to this matching?
DX,
DX, okay.
XC,
DX, XC, okay,
then
wait.
CV.
DX, XC, CV. So is this an augmenting path?
No, ma'am. CV again, it is not.
No, it's not an augmenting path.
Only DX we can take.
DX also we cannot take because
No,
X
sorry.
is a matched edge.
Yes,
X
yes.
is a matched vertex. So DX, XC, CV, they are not augmenting paths because they are not ending with a matched vertex. So in this case, the matched vertices are A, V. They are not ending with an unmatched vertex. In this case, matched vertices are A, V, B, W, C, X. So they should start or end with these four vertices. So these two are not augmenting paths. So can anybody else give an augmenting path? So is there any augmenting path with respect to M3? There should be an augmenting path, right? If there is no augmenting path, then we'll have to claim that this is a perfect matching. But is sorry, this is the maximal matching. So is there any augmenting path with respect to M3? Yes, Vinayak. Vinayak. Yes.
Ma'am, why we take the XC in augmenting path?
Yes. So XC is an augmenting path because what is the augmenting path? It should start with an unmatched. So in this M2, We just have WA and VB. So this
Okay.
path is starting with an starting with an unmatched vertex and ending with an unmatched vertex. So our
Oh,
augmenting path can have just one edge.
okay, 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 clear.
So now yes, so if you are not able to construct an augmenting path of more than one edge, do you think there is any augmenting path with just one edge here for M3?
Ma'am, dy, we add a dy.
Yes, correct. So dy is an augmenting path. Why is with the same reason.
Yes.
D is not an unmatched vertex. Y is also not an unmatched vertex. And what is the symmetric difference now? We just take the union
Union of that.
xc dy. Now, do is this a perfect matching? Oh, sorry, is this the maximal matching, or do we have an augmenting path with respect to this matching also? Do we have an augmenting path with respect to this matching? Again, it is
Ma'am,
Yes, ma'am.
is it dy, ye?
okay.
Again,
So you are saying ez.
EZ we can take again with this same.
Yes, we can just we if it is starting with ez, then it is just ez because there is no matched edge from z, right? So ez is a augmenting path with respect to v4, and then the symmetric difference is this. So we have these five edges. So now have we got the maximal matching?
Yes,
Yes. Now there are no unmatched vertices. So there are no unmatched vertices. So there can be no augmenting path. Therefore, this is a maximal matching. So is everyone clear how we arrived at this maximal matching? So is this
Ma'am,
algorithm?
ma'am,
Yes.
ma'am, Z and DY, it is a augmenting path for the set M4.
So what is EZ? What is the next vertex? Not what is the next edge? EZ,
ZD DY
DY,
YE.
Y. So see, uh, it is first of all it is not a path because it is starting and ending with e, and secondly ez is an unmatched vertex. So it augmenting path is an alternating path between unmatched and matched edges, and dy is not a matched edge. Sorry, ez, after ez you cannot go to dy. It is not a path only, right? If it is a path, ez, you have to go to some vertex from z. So ez dy is not a path.
Ma'am,
Ma'am,
I have a doubt.
is it
Yes.
Here, taking this E set, before taking this E set matched set,
Yes.
can I say the augmenting path after the M4? I think the
Yes.
Vinayakam sir question is that uh,
What path you are taking? Yeah.
EY DZ. E is an unmatched vertex.
Ey
EY, Y is a
dz.
matched, and D is it. Before taking this E is it an augmenting path?
Just ey
Um,
and
uh,
dz, or something else also.
EY D. EY D is it. Yes, that's all.
No, it is not because ey
okay.
dz. So
Ma'am, this is the length two, na? We have already discussed the length is not odd.
okay, yes, yes. Plus also it is not a path, right? Ey dz is not a path.
Sir, Y is it, sir? EY D is it?
Ey, so the other edge. Okay, you are saying yd and dz. This you are saying, right?
Yes, ma'am. Yes, ma'am. Yes, ma'am.
Yes, that is an augmenting path. That is correct. dy and dz. That is an augmenting
D
path.
is it?
Yes, yes. This is an
Okay.
augmenting path. So
Okay.
augmenting path.
Before,
So you can
instead
take.
of choosing directly is it, can we take this and then we
Yes,
do
yes, yes.
union?
Yes. So okay. Okay. Now I got it. Sorry. So this was P4. This was P4. From this you were getting this matching. Now you suggested me a different augmenting path. Different augmenting path is EY, YD, and DZ. So now if we take the symmetric difference of this, then what will we get? M5 as, so dy is a common edge here. So the symmetric difference will be WA, VB, XC, EY, and DZ. So, so instead of these two, now you are getting these two. So that is also correct. So the green one is also a maximal matching. So yes. So you, if you'll take a different augmenting path, you'll get a maximal matching, but you are getting a different matching. Both the answers are correct. Sorry for the confusion earlier. So now this was your question, right?
Yes, ma'am. Yes, ma'am. Yes, ma'am.
Okay.
It's clear now. Thank you. Thank you.
Okay. Okay. So if so, has everyone understood the algorithm? There, should I go on to next question, or should I go one do a similar question of algorithm like of this? Like there's one more graph, or can we move on to the next question?
We can solve one more
One
question.
more, ma'am. Similar one.
Similar one more. Okay. Okay. So the second graph is this. Yes. So first of all, I'll just name the vertices so that it is easy. A, B, C, D, E, and U, V, W, X, Y. Okay. So now we have to find maximal matching using an augmenting path algorithm. We start with M to be empty set, M0 to be empty. So so what is the M0 is empty. So what is the augmenting path with respect to M0? So since there are no matched vertices, we can take any of the edges. So let's take AV. Now if we look at the symmetric difference, then it is M1 is basically AV. Empty set and AV ka symmetric difference is AV. Now can you give me an augmenting path with respect to M1? So M1 is AV. So augmenting path with respect to this matching. So all the other vertices other than A and V are unmatched. So augmenting path should start with an unmatched vertex, end with an unmatched vertex, and should alternate between unmatched and matched edges. So give me an augmenting path with respect to this matching.
WA, AV,
Hmm. Okay.
then VC.
WA, AV, and
VC.
VC. So that is correct because W is an unmatched vertex, C is an unmatched vertex, W is an unmatched vertex, C is an unmatched vertex, and WAVC are unmatched edges and AV is a matched edges. So all the properties are satisfied. So now we'll take next matching will be the symmetric difference of this. So only common thing is AV. So the symmetric difference is union and we remove the intersection. So it will be just WAVC. So this is our next matching, which is WAVC. So now these four vertices are matched. All other vertices are unmatched. So now we have to construct an augmenting path with respect to M2. So can you construct an augmenting path with respect to M2? So all the other vertices other than green, it should start with that, end with that, and alternate between matched and unmatched edges. So give me an augmenting path with respect to M2.
So
Madam, CW,
EV.
Okay, CW,
no, 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 EW,
CW is not an edge. Yes, EW,
EW, WA.
WA.
This, okay, no, it is not correct.
No, this is not there.
This cannot be there because you have to go end with AV.
EV.
Okay, so first wait. So EW, WA and A. So EW, WA and AV. This is not an augmenting path because V is not a unmatched vertex. So we cannot
Yes,
take this
yes,
to be an
yes.
augmenting path. So now what is the next thing? So what can be the augmenting path then? So somebody was giving me an example. Anupam, you were saying something. So give an augmenting path. So anyone can.
Ma'am, we can take single also. DX we can take.
Yes, we can take single also. So if we take dx, it is starting with an unmatched vertex, ending with an unmatched vertex, and so we can just take dx. Good. So now if you'll take the symmetric difference, since there are nothing in common, so it is just the union. So M3 is this WA VC dx. So this is our M3. And these are matched vertices. So now, do we have any augmenting path now with respect to M3?
XD. Sorry, YD.
YD we cannot, YD, okay. Just YD or anything else?
No, no.
YD is not an augmenting path because it is not ending with an unmatched vertex. So, is there any augmenting path with respect to this matching?
Ma'am, this is the maximum one.
Okay, if you are saying it is a maximal one, you have to give me a reason why it is maximal one.
Because we are not getting any augmenting path.
Okay. So how did you know? How do you know that we are not getting any augmenting path? You checked for each vertex.
Yes, ma'am. Because it is easy graph, so we I have checked with each vertex.
So yeah. So see. So yes. So basically, what? So if we are not getting any augmenting path, then this is the maximal. So let's see. Suppose so we know that if it is an augmenting path, it should start with an unmatched vertex. So let's say first of all it starts with u. If it starts with u, then there's only one possibility. Then you should go to d. But now it cannot end at d because d is already matched, so we have to go with some unmatched edge, so we have to go to dx, but this is not possible. Now dx there is no edge, so we'll have to end at, so any path, augmenting path possible from u is ud and dx, but this is not an augmenting path, so our augmenting path cannot start with vertex u. Now similarly you check for b. So for b it is starting, so now for b also there is just one option. It should go, b it should go to w. Now for w it cannot end at w because it is already matched, so it has to go to some matched edge. So from bw, wa. Now it cannot end at a, so the other possibility it has to go to av. It cannot end at av either, therefore it will go to vc. but it'll have to end at C, but this C is not a unmatched vertex, so this is also not an augmenting path. So from B also we are not getting any augmenting path. And similarly you can see from Y and E also we are not getting any augmenting path. So there is no augmenting path with respect to M3. Therefore this is maximal matching. So is it clear to everyone? So for U and B, I have shown you how to check. So similarly, you could check for Y also. So for Y, there is one option. You go to YD and then DX. This is the only possibility, and this is also not possible. And for E also, the only possibility is EW, WA, AV, VC. And this, so for if it is starting with E, it will be EW, WA, AVVC. There also it is ending with a matched vertex. So you see there is no augmenting path with respect to this matching, and therefore it has to be a maximal matching. And by the algorithm we are arrived at maximal matching. So is it clear to everyone this question? Any doubts in this question? Okay. So if there are no doubts in this question, good. So now this is a bipartite graph. It does not have a perfect matching. Therefore, Hall's condition is also not satisfied. So can you so from now from there's one way we have conclude from augmenting path algorithm that it does not have a perfect matching. But can you try to find try to conclude the same thing using Hall's theorem without using the algorithm, that this does not have a perfect matching? So does everyone understand what you have to do? So basically you have to, if this is X, this is Y, give me a subset of X such that order of S is strictly, order of S is strictly greater than neighbors of S. If we have such thing, then we'll have that it will not have a matching which saturates X. So can you find such S? So I'm just trying to conclude the same thing using Hall's theorem.
DE. S
Uh,
is equal to DE, which has 656 neighbors.
sorry, S is equal to, I did
DE.
B E.
D.
Okay, I get it. Okay, so you are saying S equal to B and E, right? S equal to B E. So what is,
D for D and E. Okay.
Ma'am, if we take S is equal to W and D, so neighbors are more, ma'am.
but you cannot take from different partition. You have to take from one partition. So first
Okay.
of all, if you're take so firstly I'll clarify this one, then I'll S is, if you are taking S equal to B E, then the common neighbors of BE are VW. So you cannot, NS is coming out to be EVW, right? So this is, it is not satisfying this condition. So this S is not correct. And secondly, second S is given as BW. This is also not correct because Hall's theorem says you have to find. So you have basically finding a matching that saturate X or Y. So they should belong to one component. So both these S are incorrect.
So, ma'am, if we take S is B and C, so neighbors are more, ma'am, for that.
If you take S equal to, but
Madam, BCE.
if you are
S
taking,
is BCE.
okay, S is B C E. Okay. If S is
N
B,
of
okay, okay. So S, now if we are taking S as B, C, E, then what are the neighbors of B, C, E?
VW only, ma'am.
VW only. Yes, good. So now, so now we have, it is satisfying this condition and therefore it is correct. So we see that using Hall's theorem also we are able to conclude that this won't have a perfect matching. Good. So is it clear for everyone?
Ma'am, if we take S as D and C,
B and
D,
C.
D,
Yes.
D and C,
Okay.
so neighbors are X, W,
S is BC,
D, ma'am, D, C,
DC. Okay. If S is DC, then neighbors of D and C are
X, U, V, Y, sorry, U,
D and
V,
C. So
W,
basically X, if you are taking S to be D and C's, then yes. So VWXY. VWXY. Yes. But this is satisfying the Hall's condition then, right? So from this you cannot conclude.
no, ma'am. Why it is satisfying? S has only two and N has four.
Yes, so the Hall's condition says that if order S is greater than equal to NS for all S, sorry, wait, sorry, order, so I messed, order S
Ma'am,
is
less than
less
or
than
equal, ma'am.
equal to, NS, if this is true for every S, then by Hall's theorem, it has a matching that saturates X. It has a matching that saturates X. So in this case, so this is not a counter example, right? So you cannot use this to say that it does not have a matching which saturate X. You have to give a subset of X such that order of S is strictly greater than order of NS, and he has given this S as BCENS. So S has three members, but they have only two neighbors.
Yes. True, ma'am.
Okay, so therefore hence it is true, hence it does not have a perfect matching. Okay. Okay, so first of all we'll go to, yes, so this was on matching. Now there are few more concepts which were introduced. First one was vertex cover. So what is a vertex cover? Vertex cover is a subset of vertices such that every edge of a graph is incident to at least one vertex of S. Okay, so for vertex cover, it is we have to choose vertices in such a manner such that every edge has at least one of the endpoints in S. So in this example, you can see BCD is a vertex cover because if you take any edge in this graph, they have one of the endpoints in this. But if you take A, B, but if you take A, B, and C, I am saying that it is not a vertex cover. So can you tell me why A, B, C is not a vertex cover? A, B, C, it is not a vertex cover.
Edge DE has no vertex in this set.
Yes, good. So they have an edge DE which has none of the endpoints in this. So we say we have this that this is not a vertex cover. So this is the definition of vertex cover. So now Koenig's theorem says that if we have a bipartite graph G, then size of maximum matching has to be equal to size of minimum vertex cover. So this has been proved in class. So in a bipartite graph, to find a size of maximum matching is same as finding a size of minimum vertex cover. So this is Konig's theorem. Then with vertex cover, then we also have a notion of independent set. So independent set is a set of vertices such that there are no edges between vertices of S. So if we have suppose if we have this bipartite graph, since we have no edges within these, within within A, so A is an independent set, and similarly B is an independent set. So in this example, can you give me an example of independent set in this graph?
Ma'am, if we remove that vertex cover from entire, then it is independent.
Yes. So so vertex cover is B C D. So you are saying A E is an independent set.
Yes.
Yes. And we can see there is no edge between A E, so it is an independent set. Correct. So so A E is an independent set, and therefore the and so he has used basically this theorem, that if S is independent, then the complement of S will form a vertex cover, and similarly it is a other way around also. So S is independent if and only if its complement forms a vertex cover. And then we have this theorem that if alpha g is the size of maximum independent set and beta g is size of minimum vertex cover, then alpha g plus beta g will be sum of alpha g and beta g will equal to the number of vertices. So similar to vertex cover, we have a notion of edge cover. Edge cover says that edge covers is basically set of edges such that every vertex is incident to at least one edge. So vertex cover, in vertex cover we were saying that we have to choose those vertices such that every edge is incident to at least one vertex. In edge cover we are choosing those edges such that every vertex will be adjacent to at least every vertex is adjacent to at least one edge. So in this example, can you give me an example, in this example can you give me a edge cover, example of edge cover? So basically you have to select or select some specific edges which is covering all the vertices. So can you give me an example of edge cover in this graph? What about AB? So what about this? AB, DC and CE. Is it an edge cover? So A, so we have to check that every vertex should be adjacent to at least one edge. So A is present in this edge, B is also present, C is also present, D is also present, E is also present. Therefore, it is an edge cover. What?
Ma'am, in edge cover, there
Yes.
is, it may be isolated or it should be continuous path.
uh, there is no such condition. You just have to give me some set of edges which is which such a set of edges such that every vertex is covered.
So can this is the example, ma'am? You write please
Huh?
AB,
AB,
AC,
AC,
D, DE,
DE.
and DC.
Yes, this is also an example because it is covering all the edges, covering all the vertices. Yes, this is also an example.
But this in this, ma'am, you see there is a connectivity also.
Yes, yes, yes.
But in your example, they were edges were disjoint. They are not connected.
Huh, so that is possible. So edge cover can be connected, disconnected. It is it, but the only so if you'll see, if you collect all the edges also, then also it will form the edge cover. You can edge cover can there, if you take all the edges, that will also form an edge cover.
There is no minimum or maximum criteria in that. Minimum
No,
maximum.
no. So edge cover is anything set of edges which is covering all vertices. But so definition of edge cover is that. But we might be interested in finding the minimum edge cover. Then we'll have to find the edge cover which has least number of edges. Okay. So when we are saying just edge cover, we are talking about collection of edges with such that every vertex is incident to at least one edge. So your example is covering also all the vertices, therefore it is an edge cover. But it is not a minimal edge cover, because the original example that I have has only 3 edges.
No,
Okay.
ma'am, but in your example, that is not a graph. That is disconnected graph.
Ha,
That is
so
a graph, but that is not a connected graph.
so you need, in an edge cover you need not need a connected graph. You just need a set of edges such that such that every vertex has at least every vertex is present in one of the edges.
Okay, okay.
We don't require any type of connectivity. And so we see that size of maximum independent set and size of minimum vertex cover sum up to n. And similarly, if we look at a graph without isolated vertices, the theorem says that size of maximum matching and size of minimum edge cover will also sum up to the number of vertices. So these are the theorems. Now let's solve some questions. So first of all, any doubts in any of the definition? Independent. So we have discussed four things: independent set, vertex cover, edge cover, and matching. So any doubts in any of the definitions of these? Okay. So if there are no doubts, let's look at the questions. This is done. So first of all, so we had this theorem. We had this theorem for bipartite graph. For bipartite graph, we have this theorem that size of minimum vertex cover is equal to size of maximal matching. So now the first question is it true or false that this is true for bipartite graph? We know that. But is it true for any simple graph G also? Non bipartite graphs also. That size of minimum vertex cover should equal to size of maximum matching. What do you think? Is it true or false? Okay, okay, maybe let's do look at some example before claiming this. So suppose I have kn, or let's say k3. I have to find all these four things. So k3 is triangle, alpha g is maximum independent set, size of maximum independent set. So what do you think is size of maximum independent set for this? For k3. So do you understand the definition of maximum independent? First of all, independent set. Independent set is basically set of vertices such that there are no edges between those vertices. So what is the size of maximum independent set for k3?
There is no independent set, ma'am.
Okay. Why? Why there is no independent set?
And there is a edge between every pair of vertices, ma'am.
Yes, that is true. So there is no independent set of two vertices. But what if we just take set S to be A? Singleton set is trivially independent, right? Because if we have just one vertex, there cannot be any edge within that vertex. So the size of maximum independent set is 1 here. Is it clear?
Yes.
So for Kn, what will be the size of maximum independent set? So same argument what he said. There is an edge between any two vertices. So an independent set cannot have two vertices. Therefore size of maximum independent set for Kn is 2. Kn is 1. So is it clear? So size of maximum independent set is 1. So what about size of beta g? Beta g is, this was max independent set. Beta g is minimum vertex cover. So what is beta kn? Minimum vertex cover. And also we have this theorem that alpha
One
yes, yes.
set containing A, so it's one.
So you are saying minimum vertex cover is A.
And minus edge minus 1.
So okay. So see, if you just take it to be A, then there's this edge BC, which is not which is not so S equal to A cannot be a vertex cover, right? Because edge BC does not have any endpoint in S.
Okay, then A comma B.
Yes, A comma B is correct. So now for K3 it is coming out to be 2. Can you generalize for Kn?
Edge minus 1, ma'am.
What minus 1?
Total edge minus 1. Or
Total
n.
edge.
Yes, n or minus 1, yes.
N is not the number of total edges. N is the number of
Vertex,
vertices.
vertices.
Yes, it will be number of vertices minus 1. Right? So either you can use this theorem that alpha g plus beta g is equal to order of vertices, or otherwise you can say that so if you don't want to use this theorem, otherwise you can say that if we take less than n minus, so we have to look at the minimum vertex cover. So if I am taking less than n minus 1 vertices, so there are two vertices left in the complement and there is an edge between those two vertices. So that cannot be a vertex cover. So basically if I am taking any set of vertices less than n minus 1, then I have at least two vertices which are left out. And those two vertices has a edge between them. Therefore, it cannot form a vertex cover. Therefore, we see that size of minimum vertex cover for complete graph should be n minus 1. So is this argument clear to everybody why it is so? Either you can use the theorem or the reasoning that I have given. Any doubts? Okay. Now alpha dash g, this was the size of maximal matching. So what do you think? So suppose I have this K3. What is the size of maximal matching here? What is
One,
this?
one, one.
1. Why? Why it is 1?
Because if we do another, then it is from one it is going to two.
Yes. So basically, a matching cannot have edges, cannot have two edges with a common vertex. And if we have done it for one, and if we take any other edge, we'll have to repeat a vertex, which is not allowed. So therefore, alpha dash k3 is 1. So what about k4? What is the size of maximal matching for k4? What is the size of
2, ma'am. 2, 2.
two?
Two.
2. Okay, good. So we can take 2. And we have, since we have covered all the vertices, so we cannot have a bigger matching than this. This is a perfect matching. Now, okay, what about K5? What about K5?
2.
K5. 2. Yes. Again, why it cannot be 3? Why it cannot be 3? Why is it 2? Why it cannot be 3?
Madam, it has a odd number of vertices. One side is 2 and another one side is 3, ma'am.
Yes, because
So what 2?
if we add any other edge, then we have to repeat a vertex.
Yes, ma'am.
So can you generalize now? Alpha dash kn. What it is? Suppose alpha dash k2n, say. What is alpha dash k2n?
N, ma'am.
Okay, n. Good. And what is alpha dash k2n plus 1?
Which is,
Again n, right? Because if we are
yes,
taking
yes,
n,
ma'am.
we have covered
Yes,
2n vertices and we have just one vertex left.
yes, ma'am.
Okay. Now this was maximal matching. Okay. Now we have to find out beta dash k2n. What is beta dash k2n? This is size of minimum edge cover. Size of minimum edge cover. So suppose for K3, can you give me an minimum edge cover for K3?
2.
Okay, 2. Okay. So you are saying 2. So is everyone agree why beta dash of K3 should be 2? First of all, why it cannot be 1? So it is a first of all it is an edge cover because all the vertices are covered by this. Now we have to say that it is a minimum edge cover. So that means edge cover. If we take just one edge, it won't cover all the vertices. So which is evident, right? So therefore beta dash of K3 is 2. Or since Kn is a complete graph, it has no isolated vertices. We can also use that theorem which says that alpha dash g plus beta dash g is equal to order of vertices. And we have that alpha dash, we have already find out that alpha dash k2n is n, and alpha dash of k2n plus 1 is also n. So can we find out beta dash then directly?
V cardinality of V dash minus n.
So what is the cardinality of k2n, vertices of k2n? So what is beta dash k2n?
N.
N. Yes, because we have 2 n vertices. And similarly, beta dash of k2n plus 1. This is 2n minus n. Similarly, what will be beta dash of k2n plus 1?
N plus 1.
N plus 1. Good. Because we have 2n plus 1 vertices, and we have already seen that maximum matching has n maximum matching size has n. So 2n plus 1 minus n will give us n plus 1. Also, so I'm just wanted to clear out this, that alpha g plus beta g is equal to order of vertices always. But this condition, that alpha dash g plus beta dash g is equal to order of vertices, this is true. This we can imply only when G has no isolated vertices. So now if the definition of all these four terms are clear, then we can do other questions. So is it clear? Is there any doubt between the definition of any of these four terms? Alpha G, beta G, alpha dash G and beta dash G. If no, then we can move on to the last question, which we were doing. Okay. So now, so for bipartite graph, we have this Koenig's theorem, which says that size of minimum vertex cover is equal to size of maximal matching. Now the first statement is saying, is this true in general? So what do you think? Is it true for general graphs also? So what do you think? Is it true or false? So for Kn only you can check if it is coming out to be same or not.
So now,
Huh?
for Kn,
Hmm.
we have to prove for other graphs also. So it is, we say uh, it is a false statement then, because we have to then give counter for every type of graph.
No, no. So if you give me just one counter example, then we'll say it is false, right? So the statement is saying in any graph G, so the statement is saying this is true for all graphs. So if you can give me one graph for which it is not true, then the statements become false, right? Is it fine? So if we take G to be K3 only, our size of minimum vertex cover, it was coming out to be 2, beta G was coming out to be 2, and alpha dash G was coming out to be 1. Therefore, this statement is false. So does everyone understand why first is false?
Ma'am, which graph, ma'am? Which graph this is false?
K3.
Okay, okay.
Yes, true. So it is false.
Yes, K3. So minimum vertex cover. So see, minimum vertex cover was coming out to be 2. We already calculated, and maximal matching was coming out to be 1. So this is false. Now second question says that in any graph G, size of minimum vertex cover will be greater than equal to size of maximal matching. Is it true or false? So this statement is true, because suppose M is a matching. Suppose M is maximal matching with K edges. Then if S is a vertex cover, so we have this K edges in the matchings, and matchings will have all the disjoint vertices. So if S is a vertex cover, then S will have at least one vertex from each edge in matching. So any vertex cover will have at least k vertices. Therefore, beta g is greater than equal to alpha dash g. This is the size of minimum vertex cover. So minimum vertex cover will also be a vertex cover, and it should have at least k vertices. So is it clear why 2 is true? Is it clear why 2 is true? Any doubts? Okay. If not, now what about 3? If order of vertices is n, then beta dash g should be greater than equal to n by 2. So beta dash g was the size of minimum edge cover. Yes, question? There's a question? Yes, somebody was asking some question?
No, ma'am. Sorry.
Okay, it's okay. So for third, what do you think? Is it true that size of minimum edge cover should have at least n by 2 vertices? So what is a minimum edge cover? So it should be edges. It should be edges and it should cover all the vertices. So basically, every vertex should have at least one. Every vertex should be present in at least one of these edges in that edge cover. So do you think this is true then, that if we have n vertices, then
It is
size of minimum edge cover should be greater than equal to n by 2?
it is
Yes, Anupam.
true, ma'am. It is true.
Why? You have to give a reason why it is true. So the answer is true. Why but?
We can give only one example, but then we cannot prove this by what you said, 10 examples.
Yes, yes. We cannot prove it by examples, but if you are saying it is true, it has to be, you have to give an argument which work for all graphs.
That is what I took one example in which it is coming true, so that is why I said it is true.
Okay, okay. So okay, but it is but that doesn't mean that it cannot be false. So why it is true is basically, so if it has G has n vertices, right? If G has n vertices, so every edge cover two vertices, right? So if we have an edge cover, if we have an edge cover with less than n by 2 vertices, say k which is strictly less than n by 2. So what is the maximum number of vertices? What is the maximum number of vertices will that edge cover cover?
2k,
Yes,
2k.
2k. So is covered by that edge cover is 2k, which is 2 raised 2, which is strictly less than 2n by 2. So 2k is strictly less than n. So any edge cover which has less than n by 2 vertices cannot cover all the vertices. Therefore, it should have at least n by 2 edges. So is it clear why it is the third statement is also true? Any doubts in the third statement? Is the proof clear?
Yes.
Okay, so now fourth. So fourth is if order V is n and and we have no isolated vertex, that is degree of each vertex is greater than equal to 1, then can we say that alpha dash g should be less than equal to n by 2? So in third we have shown that beta dash g is greater than equal to n by 2. Now we are given a graph g with n vertices and no isolated vertex. Degree of each vertex is greater than equal to 1. That means we have no isolated vertex. Can we say that alpha dash g should be less than equal to n by 2? True or false? Can we use some theorem to conclude this? Hint. Hint, we can use one of the theorems that we have done in
Most
class,
of the sum, ma'am, we have said it is equal to cardinality of V,
which is n. Yes.
which is n. So now, if one is greater than n by two, definitely to balance other, it should be less than n by two.
Good. Very good. So alpha dash g plus beta dash g is equal to n. This is because G has no isolated vertices. And we have already shown that beta dash G is greater than equal to n by 2. So alpha dash G is equal to n minus beta dash G, and beta dash G is greater than equal to n by 2. That means n minus beta dash G will be less than equal to n minus n by 2, which is n by 2. Therefore, we get that alpha dash G is less than equal to n by 2. So, third is also true, fourth is also true. So, are all these four statements clear to everyone? Any doubts?
Yes.
Okay. If it is clear, then this was the last question today. If you have doubts, you can ask. Otherwise, I'll end the meeting.
Thank you, ma'am.
Okay.
Thank you, ma'am. Thank you.
Okay.
Thank you, ma'am. Thank you, ma'am. Thank you.
Okay.
Thank you, ma'am. Thank you.